Hello and welcome to the practical session of the Copernicus Black Sea training. My name is Marcel from the Helmholtz-Zentrum Geesthacht, Germany. I am here on the behalf of our production unit consisting of Joanna Staneva, Arno Behrens and Gerhard Geier, which have been introduced during the first session. I will show some examples how to use the Black Sea wave model data, which we provide to the Copernicus website. First of all, here are some general notes how to use the Jupyter Notebook, the table of contents. I will go into detail what we are going to plot at the respective section in the code. I think this makes it easier to follow my talk. In the beginning, I will introduce the data we will use. So our production unit delivers two different kind of data sets to Copernicus. The first one is the forecast data set, also called the near real-time data. We upload this data on a daily basis from a wave model which is also run daily. And we deliver 1 hindcast day and 10 forecast days. If you click here, you will be linked to the Copernicus website where our product will be displayed. Here are some informations and an overview of the forecast dataset, the available domain variables and the temporal coverage, which is here. If you want to know more about this product, we refer to the product user manual where you find technical details, or to the quality information document where you find model analysis and validation. Here you see an overview of the data we will use in our exercise. This is the geographical range, which covers the whole Black Sea, which is also shown here. We will use a bit more than 1 day of data, so it's 1 day in January 2019. We will use 3 variables: the significant wave height, wave direction and mean wave period, and the file is in total 28 megabytes large. The second dataset we will use and which we provide is the reanalysis dataset, also called the multi-year product. The same again as before. Maybe some words about the difference of the two datasets. As you see here, this dataset covers roughly 2 years of data, and so from 2018 until present. In contrast, the multi-year product covers the years 2002 until 2018. So the last year is not provided. However, the model is run with improved wind forcing and slightly different physics, which you will find again in the product user manual and quality information document. And this data set is updated twice a year. So here you see the details about the data set we will use for the exercise. In contrast to the new real-time data set, we only use a geographical range of 0.5 times 0.5 degrees in latitude and longitude direction. But the time period is much longer. It's not only 1 day, but 10 years. So from 2008 until 2018. We download the same variables, which results in a total file size of 300 megabytes. So this notebook is in the WAV folder, and the data is stored in data, and the data set A is the new real-time data and introduced as a first data set, and the data set B is the multi-year data set, which is the latter. So some points about how to download the data. So first of all, you have to make your user credentials on the Copernicus website. After doing this, you have three possibilities to download the data. So the first one is to use the FTP server. On the FTP server, you can access the data as it is delivered to Copernicus, so in our case in daily files. Then you have the possibility to download the data via this Motu client. And the third option is to use the Copernicus website. It's quite comfortable because it has a graphical user interface and you can select the variables and time range and so on. However, this is restricted to, I think, 1 or 2 gigabytes of data. After downloading the data, you can list the files in the folder data and see if the files are available. It's the folder I've shown some seconds ago. So again, the same. Here you can check the Python version you're using. It should be 3.7. If not, I will comment on it in some seconds. So for this exercise, you need these modules listed here, which you can install using this line. However, this is only necessary if you are using your local Python installation. So for the Jupyter Notebook, this is not necessary to install. So first we will import all needed modules. For example, this one, this switching off warnings, and now you import the rest of the modules, and if an error occurs in this line, you have to set this path. For example, if you're using a Python version older than 3.7, you probably will get an error. However, not in the Jupyter Notebook, but only if you're using your local installation. Here we name the variables for the file names, defining functions for creating paths and getting a certain range of a variable, decomposing the wave direction, and naming the paths to the input files. Here we list the folder in which we are creating the data and output path if they not exist, and list the created folders and their content. Okay, now the actual code for the preparation of the plot begins. So I will now explain some details of what we will show. In the first exercise, we plot fields of the whole Black Sea domain of significant wave height as instantaneous fields. Overlaid are vectors of the wave direction. Why we chose this period, we will see later. So now we will use the dataset A, which is the near real-time data. Open the dataset, and by the way, we are using netcdf. I will not go into detail here. There's sufficient information somewhere else. This is the principal structure of a netcdf file, where you, for example, find the dimensions. This is the length of the dimensions, latitude, longitude, and time. So we have 28 time steps, and because we have hourly instantaneous data, we have 28 hours of data. The coordinates, the variables we've downloaded, I already mentioned these variables, and the global attributes of the file where you can find further information. Again, the variables and the coordinates, and now we name them for Python. We name the coordinates and the variables. And now a slightly longer code cell is coming. So I will not go into detail and in these plotting cells. You can do this when you will do the suggested tasks. However, some short comments about the most important lines. So here we load the data which we will use. So this is the wave height and the wave direction data. So wave height and wave direction. The longitude, latitude, and time arrays. If we had a 3D variable, this would be true, which is not the case. These are the limits for the plots in a geographical sense. This is the range of the color bar. So this refers to the wave height, which ranges between 0 and 6.5 meters. The time is from January the 3rd until January the 4th, from 7 p.m. to 9 p.m. We will also subsample the time steps. So we only use every third time step to reduce the number of plots. And for the vectors we will use every 10th grid for better visibility. Some information about the time variable. And now we are preparing the plot itself. So please go through it by yourself. I think there's no complicated line. Here the subsampling is done in the actual plot. Here we prepare the data for the plot, which is on a regular grid, and the data is plotted here for the significant wave height. For the wave direction, we have the data in degrees, which have to be decomposed into u and v component. What is important to mention here is that that all Copernicus directional variables are given in coming from direction. However, it is in oceanography it's more common to plot it in going to direction, and this transformation is also done in the in this function. This function you will find here. The plot of the vectors is done here with the quiver command. Here meridians and parallels are plotted. The color bar, countries, titles, and so on and so on. And after setting up the plot, we can execute the cell. So this is the first plot of the first time step. So it is January the 3rd at 8 p.m. In the background you see the significant wave height to which the color bar is related, so here the range 0 to 6.5, and overlaid the vectors of wave direction in going to direction. So you can see here where you can see wave heights here of about 3 meters, which are even higher than normal wave heights. We will come to this later. And now every third hour you will see one plot. The wave height increases, and the maximum of the wave height moves from the western into the eastern basin, which took 1.5 days approximately. And now it's your turn. You can try, for example, changing the shown area or minimum or maximum values for the significant wave height and so on. You will find here examples, and yeah, feel free to change the code. Now we are coming to exercise number 2. If you have executed the commands of exercise 1, you don't need to repeat this in terms of importing the modules. However, we will use the Waverose module, which has to be imported. So this block has to be executed again. And the functions are also the same as before. So we will proceed here in 4.3. For this exercise we will use the dataset B, which is the multi-year dataset. And so open the dataset. And here we again see details about the file. So in contrast to the dataset A, we have only 19 and 15 grids in latitude and longitude direction, but we have 87,000 time steps, which is quite long, so 10 years of data. Doing the same as before. And now again some words about the exercise itself. So in exercise number 2 we will plot a so-called Waverose. The Waverose is a statistical plot showing the wave height and the wave direction in one plot as a average over a time series. And we will do this at one specific location given here, 28.3 and 43 degrees in longitude and latitude direction, which is roughly so. Which is roughly somewhere here. And with this plot you can see, get a first insight in the mean or the average conditions in at a certain position in the Black Sea. So now we extract the wave height, wave direction. As an output you see some information about the variable. Then we set the minimum and maximum wave height to be shown in the plot, and the step of wave height, so 25 centimeters in this case. We also have to set the number of directional bins, which are 15, or no, which are 15 degrees long and in 24 in total. As mentioned before, the direction is given in coming from, but to get going to, we have to wear the directions about 180 degrees, which is done here. This is the preparation of the windrows. I will not go into detail. You will find a lot of information in the internet and user manual. More interesting is to see the outcome, which is prepared here. So this is the Waverose, which we have prepared from our data. This is the step or the ranges of significant wave height, shown here as colors. And you also see the wave direction, which is the shown here. So the mean direction is into the southwest, and these numbers are the percentage of occurrence of a certain direction, which is the length of these bins here. And as you can see, the main wave direction, which is similar to the wind direction, is to the southwest, and the mean wave height is somewhere in this blue range, so maybe up to 1.5 meters. Between 0.5 and 1.5 meters is the usual wave height in the Black Sea. In our exercise 1, we have seen that there were waves of over maybe 7 meters, which is a very exceptional event. You see that waves over 5 meters are very rare, at least in this western basin of the Black Sea. It's also possible to show the occurrence of certain directions not in terms of percentage, but also in total numbers, which is given here. This is the size of the table from which the Waverose is plotted. So we have 18 bins for the significant wave height here, and 24 bins in the direction, so here in this direction. This is the table, and maybe you want to use this table for another purpose, doesn't matter for what. So you can also, these are the single time steps, you can also save this data as a CSV file and use it for, or in other programs and programming languages. This is the file, and you find this file here, and you can have a look at it. Same again, you can change the parameters as you would like to. Here are some suggestions what could be changed. Feel free to play around. And that's it with exercise number 2. In exercise number 3 we have 2 sub-tasks. You starting with the previous exercises, you don't have to import new modules or functions, and you can start again at 5.3. So for the first task in exercise 3, we will use dataset A, the new real-time dataset. Open it, getting the same info as before. Now we additionally use the wave period named here, and the period is needed to plot the wave power. The wave power is not an output or standard output which can be obtained from the Copernicus data sets. So if you are interested in wave power, which could be interesting, for example, for artificial constructions like dikes or buildings, you can estimate the wave power by using a simple formula, which is given here. 0.5 times wave height squared times the period of the waves. So the rest is the same as before, and this is also the same, the preparation of the plot. Nothing new. I think we can skip it and have a look at the plots. Maybe a bit too small. But if you want to have a look at the figures after plotting them in the notebook, they are also saved in the out folder, and they can be shown by Python. For example, here, this is from exercise number 1, significant wave height, and the respective plot showing the wave power, which is given in kilowatts per meter. You see that the arrows are the same, this is the wave direction, but in the background you see now the wave power ranging from 0 to 150 kilowatts per meter. And you can see the evolution of the storm moving over the Black Sea until the 4th of January. Closing them. That was the subtask 1. Now the subtask 2. For this task, we will use the multi-here dataset B, open it, and as before for the Waverose, we will plot the data at one single location, which is the same location as for the Waverose. At this location, we will compute the wave power and plot it as a time series. Which will be done here using the plot command. And now you see the time series of the wave power over the last 10 years. So what we can see is, for example, a seasonal cycle. Can be seen here. We also see some extreme events like these ones here. And what one could try to find too is a trend in the wave power. So obviously here's no trend, but maybe from further analysis one could try to find trends in terms of increasing wave power, which could be quite interesting for many users. Here are again suggestions, these ones, for changes in the plot. And a more advanced task is this one. And this plot is shown at this location. So this location is roughly here. So it's more or less in the middle of the Western Basin. And what could be interesting is to see a difference to the Eastern Basin located here. So you could try to download a second multi-year dataset using the same time period, but downloading another area, for example, somewhere here, and then investigating the difference of wave power in at least two locations and see if there's a difference. And I guess that there will be a difference, but we can talk about it during the next live session, I think at the 3rd of June. So that's it for the Black Sea Wave unit, and thank you for your attention, and try out to change the code and note questions, and yeah, see you at the next session, and stay healthy. Bye bye.